Education is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Sri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Sri Murray Lakshman Reddy, making education a positive experience. Sri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their live projects through Centers of Excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories with equipped ultra-modern audio-visual technology auditorium accommodating 1,000 plus audience.
So good morning, sir. You can go for the slideshow, sir. Hello, Ashok, sir. Hello, sir. Sir, you can unmute yourself, sir. Please unmute.
Jai Gurudev Shweta, please lift the call. Yeah. I have now unmuted. Okay.
Good morning, everyone. Welcome to the fourth day of the session, recent advancements, recent developments in the nano composite and smart materials in the aerospace industry. So we have here today our guest, Dr. B. Ashok, sir, who served at Hindustan Motors Limited, Kolkata for 3 years as a plant metallurgist and later worked in our indigenous project LCA at ADA DRDO, Aeronautical Development Agency DRDO for over 32 years in indigenizing materials and establishing material related processes for LCA. He retired in June 2019 as Scientist G and Deputy Project Director Materials for LCA Tejas. For his contribution to the national project, he won 4 national awards, including his first DRDO metallurgist to earn the DRDO Technology Pathbreaking Award from the Government of India in 2012 for his pioneering contributions to design, development, lab trials, and finally setting up India's first certified shape memory alloy plant. After retirement from ADA DRDO, he enrolled as advocate to practice law. A multi-qualified professional with BE Metallurgy from IISc Bangalore, ME Mechanical from IISc Bangalore, and LLB from Bangalore University, MBA from IGNOU, and PhD from Aligarh Muslim University, etc., a VTU PhD guide and guided 5 PhD scholars and several MTech students. He has over 70 peer-reviewed publications in the areas of material development technology and project management, associated with several professional society organizations such as IIM, ASM, ISNT, IIF, IIW, ISAMPE, Aeronautical Society of India, Bar Council of India, etc. He was past chairman of IIM Bangalore chapter and past president of IISc Alumni Association as well. He has about 70 plus publications, and the well cited publications are on International Conference on Trends in Product Life Cycle Modeling, Simulation and Synthesis at VIT Vellore, An Approach to Knowledge Management in Military Aircraft Development Project, International Journal of Research in Business Management. Chapter 21, Shape Memory Alloys for Aerospace Applications, Aerospace Materials and Materials Technologies. Volume 1, Aerospace Materials Textbook, published by Springer. Retrogression and reaging treatment on short transverse tensile properties of 7010 aluminium alloy extrusions, M. Anagappan, along with M. Anagappan V. Sampath, in the Materials and Design publication. So we have a versatile personality today with us. Sir, I would like to welcome you on behalf of Aeronautical Department of MLR Institute of Technology. Welcome, sir. Sir, please unmute yourself. You are on mute. Sir, you are on mute.
Am I audible?
Yes, sir.
Okay,
Now,
okay. I'll now start. Let me start by thanking San Professor San Shweta for the kind introduction. I also thank MLR Institute of Technology, okay, for giving me an opportunity to share with the faculty members about my work. Okay, now let me go through the brief of my some presentation. So basically, my some work was involved. Part of my work was involved in the development of shape memory alloys for our uh, fighter aircraft. As you know, our fighter aircraft is on LCA, is on Tejas, which is now in the some borders, trying to secure our some country, and it was a great opportunity for me to work. So what I thought was, let me share you my experience right from the laboratory stage, how we developed the shape memory alloy, then some prototype is on tested, and then set up an international class some production facility, which is unique in at least in is one at least I should say is on within our country. Okay, now let me go to the first slide. Okay, yeah. Okay, now before I start, I thought I should acknowledge all my some co-workers, all my seniors, all my some juniors, without whom I could not have made my work. So my first thanks is to is to our some R&D some partner BRC, and my friend Dr. Madan Gopal Krishnan. Okay, and the aircraft designers. There are numerous research workers, application engineers, throughout the world. Okay, and also my ex-organization ADA for the kind permission to share it with you. Okay. Then my agenda would be like this, because I know most of you are aeronautical engineers, and you'll be more interested in the aircraft type of stuff. So I thought, let me first give then introduction to the fighter aircraft, then the kind of some materials that is used and its evolution, then about the introduction on use of shape memory alloy, SMA is the acronym. Oh, then what are the current international R&D efforts, then what is our experience of using the shape memory alloy, and the roadmap and the current trends in the SMA use. Okay. Now, first thing is, I think being is an aero engineers, you would be is familiar with this aircraft. So this is a typical what we call as a delta configuration is uh, aircraft. You can see here it is a delta, and then okay, and then it is a tailless, and you can see this the structure of the aerodynamic is an outer structure of the is an aircraft. Okay, now we can see the control surfaces here. These are the sun elevons. Then, of course, there's a wing here, and then there is an here. There's a radome is here. Okay, and then there is an center fuselage here. Okay, and then there are okay. Then there is an engine somewhere here. Okay, which is okay. Now telling you about the kind of some materials here, because before that, what is the basic requirement for a fighter aircraft is, basic requirement is it should have maximum thrust and for a given weight, and then its also weight should be less, because aircraft industry is a unique industry, because there is an separate it's a department called the it's a weight it's a department, wherein without their sign none of the drawings can pass, because and they will be looking into the weight reductions, and yeah, and here we'll be fighting even for a couple of grams of some weight more. That is the kind of pressure we are to design the some aircraft with the lowest possible weight. Okay, now coming to the materials part, where I am sort of trained. So here we have the radome is made of aramid some composites. Because the function of the radome is to receive the microwaves, and then it is to give some indications to the pilot about the impending enemy aircrafts, okay, enemy targets. Then here we are having the center fuselage, and in the center fuselage, the skin is made of here some composites. The frames, what we call as the spurs, they are all made of this some metal, aluminum, and the fuel floors, they are co-cured some composites. Composites means we use the CFC, carbon fiber reinforced some composites, and the baffle frames are some composites, and the doors here are the sandwich some composites. And one thing unique about the wings of a fighter uh, aircraft is they also carry the fuel, because we have to save every ounce of weight or every gram of weight, And so here the wings here are having are storing the fuel. Okay, we will, and then there is no separate this one fuel tank. Okay, and what you see in the belly would be the drop tank. Okay, drop tank with the fuel, which is used for maybe for to supply to the aircraft, or it can be used for the offensive some capabilities. But when you drop the some fuel tank, it will be acting as a bomb. Okay, then you are having the landing gear. You see, and landing gear is in our case it is primarily this maraging steel, and of course the aluminum sluts. Okay, now here the landing gear makes one major role because the aircraft which is coming at very high speed has to land within few meters. Okay, and so you need to have very high braking quality. Okay, and so this is the some material that is used. And then there is a rare some fuselage which is sandwich some composite. And then air brakes are here, you can see here, and this air brakes are also some composites. Now then there is a shroud which is aluminum and some titanium frames. Okay, now this is the overall airframe materials that we are some using. Okay, now basically to save on weight, so what we have done was we have replaced the aluminum here with the carbon fiber composites. So the advantages, aluminum density, as you know, is something like 2.76 grams per cc. With the CFC, the density will be around it can be some tailor made 1.4 grams per cc. You are now saving on weight. Plus, CFC gives some major some benefits. You can do aeroelastic some tailoring, meaning you can have the strength whichever some direction you some want. You can have the some modulus whichever direction you is on want. If you take some metals, you are constrained because you will have to work with the given properties in the longitudinal as and the short transverse is on directions. Okay. Now next is again this one graphic blown up view. You can see here the top skin here. You can see the nose and okay, pitot tubes will be here. As you know, a pitot tube measures the some velocity of the air here. Then the fuselage skins, and then here you are having the glare shield. The unique feature of this one glare shield is this is made of stretched some acrylic, and then here you are having an some requirement. See, in the that is, it should not fog. Then during rains, it should not affect the some visibility of the pilot. So here we are looking for 99% plus some transparency, which is made by stretched some acrylic. Okay, okay, and then of course here there is an controls here box. HUD is on displays or here. Then is the equipment is on cover. This is the wing. As you know, wing is doubles as an fuel tank. Now here you can see the ribs and spars running here. Ribs and spars. Okay. Now these ribs and spars are the metallic part, and then you can see the rivets here, and then over this would be the some composite CFC is on layup is on complete. Okay. Now, and so it is truly and it is an composite structure, and then you can see here air intake is here. So this is the primary place where the air is being supplied to the engine here. Air intake is here, and this is the nose undercarriage door. Okay, and then fine. Then this is the fin here, and this is the radar here. Okay, and here the radar is on composite, but there is a torque tube here to turn the radar. Radar should is on okay, that is made of the is on titanium. Okay, and then you can see the statistical part. Structural weight here is some 45%. Surface area of composite will be 90%, and we are able to reduce 485 kgs. That is some significant from the fighter aircraft is a view, because the total aircraft weight will be something like 1000 kgs. Okay. Okay, then what is the material distribution within our LCA Sun Tejas? You can see 43% is made of some composites, 8% is steel, 7% is others, 2% is some titanium, 40% would be some aluminum. Now, basically, this 43% has come earlier was this, okay, aluminum. Now, you would be wondering, the topic is about smart materials. Why no smart materials are not shown here? Because they are much less than this one, 0.5%, but they play an immense functionality role. Okay, and so the if you are taking as a percentage, so they will be very less, insignificant perhaps. Okay, then I thought I should give you the some history, how the materials got sun developed. I'm sure being in the sun aero field, you'll be knowing how the aircraft design has changed. That is right from the days of Wright brothers to the present day concept. Okay, now the most advanced concept now we are trying to make is the air breathing engines, and also what is called multiple engines, and then of course the hypersonic flow, okay, engines. Okay, now if you are looking into the materials as such, the basically materials here has been in the field because of the drivers, design drivers. In the up to 1930s, right from Wright brothers days to 1930s, the primary some consideration was the static strength. Then from 30s to some 60s, what happened was they found many aircraft got some corroded, some were failing because of some fatigue. And so, apart from static strength, corrosion resistance as well as the fatigue properties became the driver. Then, from 60s to some 70s, what happened was static strength was there, corrosion resistance was there, but then when the speed of the some aircraft goes up, surface temperature also goes up. I think you'll be knowing that uh, formula. V squared is directly proportional to root of T. So no, and so we needed some materials for elevated some temperature, or properties to be stable at the elevated temperatures. And then people started talking of durability, and then damage tolerance. Damage tolerance means, suppose if you have a small crack, this crack should not lead to some catastrophic failure. We would like the crack to give sufficient warning, okay, and so repair can be done. And then we were looking for good some properties in the some thick sections, because as the section becomes some thicker, because of limitations of the some metalworking, now properties becomes less, and we would like to have an so not only higher but also uniform some properties. Then in 80s, the people started demanding more. More means they had wanted some weight savings, or I would say the most right way is maximizing thrust for a given weight. And then came the 90s era. In the 90s era, it was basically static strength, corrosion resistance, durability, damage tolerance, good properties in the some thick sections, then highly balanced some properties, And also people started looking into the manufacturability. And okay, now and now in this case, I can say you many things what I designed. Manufacturing man will come back and say, "Sir, I can't manufacture it." Okay, so the manufacturability was an issue. Assembly, how ease of assembly, assembly is on cost, and then people started talking of maintenance cost because we are interested in the in the life cycle cost. It is not the first cost. It is the is on life cycle cost, and life cycle cost includes the maintenance cost. And then in some 2000, it was the and then till now, I would say the past 20 years, we have been speaking of smart some adaptive structures, self-healing structures, and then quick response to external stimuli. Now, what do you mean by smart structures? Okay, now typically you are having a sensor. Sensor uh, uh, respond. Then after it, after the response, you will be having the action, actuation, action. Now this sensor, the sensing, responding, and then action. If it is all rolled into one, then we have these smart structures. The advantage of smart structures is the frequency of action is very fast. Okay, for high speed uh, aircraft, this is a choice. And also, you know, the present trend in the design is to have an unstable configuration. So because you can have some maneuverability only when you have unstable configuration. And to help it, you need smart structures. Okay, and then you also need self healing, means just like our human body, when a crack is there, when an sun cut is there, you will see our body is having a mechanism to heal. In the same way to heal, self healing, and these are all happening. It is not that it is like a novel or okay, it is no sun happening, and quick response to external sun stimuli. Okay. Now we'll come to the main topic, that is what are shape memory alloys, how they had revolutionized the some uh, aircraft industry as such. Okay, now they are metallic alloys. Number one, they undergo what is called a solid to solid phase transformation, and then which can exhibit large strains, recoverable states. Okay, now to give some feel, typical some material, if you take in a lab, maximum strain you can get is, I would say, 0.2%. Beyond 0.2, no. But in shape memory alloys, you can have a strain which is running up to even 7%, and then you can recover it. Something like a rubber. Okay, that is the some beauty of this. Okay, then there is, you should know some terms. There is an room temperature phase called this phase, austenite phase, which is a high temperature phase, and typically it is some cubic crystal some structure. Okay, I will not go deep into the crystal structures. Okay, then there is a low temperature phase, martensite phase. So now, other thing is, many of you would think martensite means it is a very hard. No, martensite is hard only for the iron carbon system. Okay, only in steels martensite is hard, but in other alloys like shape memory alloy, titanium alloys, martensite is a very soft phase. So now what happens here is, at the level of the crystal, there is a transformation going from this size to this size. Okay. Now in shape memory alloys, what we are trying to do is, we are trying to play with this transformation from this to here. Now, at the microscopic transformation will lead to the macroscopic change. And here, this transformation is repeatable to the atomic some accuracy. Now, I'll give an example. If you are taking some aluminum alloy, if you are so deforming it, now if you bring it to this shape, okay, now macroscopically you can bring it to this shape, but the atomic configuration will be some different. But in the shape memory alloy, the microscopic transformation, they are repeated at the level of some atoms. So we are exploiting this property. Now we come to thermally induced phase transformation. Now, how to induce the phase transformation? One is to supply the temperature. Okay, now when you supply some temperature, the phase is getting transformed. Now you have to remember some terms here. When you are cooling here, okay, when you are cooling, you have what is called Martensite start and then Martensite is on finish, because this transformation is happening in a range, because only in the case of pure metals you are having a single point some transformation, but in alloys it is in the range. Okay, and then similarly when you heat it, you have what is called austenite start and then the sun finish. Austenite is sun finish. So these are the two terms you should know, and then designers should know this because this helps in the design. Then the shape memory effect. What do you mean by it? So here, what you are trying to do is either by some temperature or by stress, you can change the phase here. Okay, and this phase, when you are removing the stress, it will be back to this, and then if it is back to the sun, okay, original sun phase. So here the atomic level and the macroscopic level, it is perfectly repeated. Okay, so here this is a thing. This is called detwinned martensite unstressed, detwinned martensite stressed, and then when you are heating it, heating means you bringing it to from liquid nitrogen to the some room temperature, that is the heating. It will come to austenite, which is undeformed. Okay. Now this is the shape memory uh, uh, effect. Now you can see the stress and strain as you supply the strain. And then, mind you, this can go up to 7%, something unique. And this 7% can be recovered back. But if you go beyond this, what happens is, instead of martensitic transformation, there will be some other transformation. And so uh, repeatability is not there. So this is how it is. Okay, now if you delete it, it will go and then it is back to here. Okay, now next. Now how engineering products you can do. Now you take what is called pseudo-elastic effect. Pseudo-elastic effect means it like a rubber, it will some stretching. But then what is happening is, uh, and then this stretch can be some recovered. Example is you take your spectacle. Those wearing spectacles like me can know the nose ridge here, what you see here, that can at times means by repeated use, that the nose ridge is not stable. It will not tightly clip your nose ridge. And then here this frames and all, because of frequent use, there will be some change. Okay, now with this shape memory alloy, it will be uh, repeatable. And these frames are already there in the marketplace. They are called as the titanium frames. Okay. Then there's pseudo-elastic effect. If you can see here, you just see here. You can either supply stress or some temperature. Here it is stress. and then you can apply strain, and then you can see here, you can recover it back just by removing the stress. You can so removing it back. Okay. Then how we use this shape memory alloys to other some areas. Okay, first I thought let me tell you the other areas, then so come to aircraft. This is the some coffee maker here. In this some coffee maker, what it does is it acts a shape memory alloy there acts as a switch, temperature uh, switch, and then here you can see one hot shower. In hot shower, I think those living in some apartments will be knowing. At times there will be no control on the sun temperature if it is centralized sun uh, uh, heating. Suddenly temperature will be high. Using okay, Satya Prasad, do you have any some question? Okay, okay. If you have questions, I think at the end I can answer. Okay. Now in this hot shower, using shape memory alloy, what you do is you choose the transformation which is somewhere at the tolerable level of 60 degrees, 70 degrees, so that the water temperature will not exceed some beyond that. Then we come to your phones. In your some mobile phones, you can see the here, and then you can see the this loop here antenna which receives some signal, and you know these antennas are highly some directional, so this will maintain the direction here no matter whatever small stress to you is on apply here, and so the you can have a good some signal receiving to the phone. Okay. Then another thing about human thing is here, the dentures. You see now you know very well if you are going to and having an some denture or you are having a clip here, it is a painful process of sitting with the dentist. Now with the shape memory alloy, you see what happens is everything is in the is on perfect place, so it will not change. So the comfort level is high. Okay. Then there are biomedical some devices. I would say nearly 80% of shape memory alloys are used in these stents. These stents you can see here, they are just like some balloon, and here these some catheter. It will be going to the prescribed place in the heart, and at the place where you need the balloon will expand, controlled. Okay, expansion means it will remove all the clogging. Okay, clogging will be removed. And in the advanced stage, you can also have the drugs which are going at a prescribed rate. Okay, you can also have inbuilt. Okay, uh, and then here you can see the spinal support. In the spinal support, when you are using shape memory alloy wires, see the spinal cord, it will be in some place. Now, people get pain only when the spinal cord moves. Now, when these wires are firmly holding the spinal cord, there will be no some movement of the spinal bones, and so comfort level is high. This is the okay. Now this is the wire, denture wire. Okay, okay. Then which was covered. Then of course most of the some production of shape memory alloys are in wire, and then here you can see kind of a resistance here. Okay, and then this is used basically for the sun temperature control, and then here this is I will be talking about it some later. Okay, this is basically how we can have an ejection system made out of shape memory alloy. Now, this is, shape memory alloys have also been used in Land Rovers. You can see the Land Rover here. It will be used for basically actuating here, actuating the rollers here. You can see here, and this is the structure. Then coming to applications, then I thought, what are the shape memory alloy systems? You are having so many alloy varieties. One of the first alloys was by the Hausner. He had found the what is called as the copper gold system. Then came here you can see okay, here is a gold some cadmium some system, then the silver some cadmium, copper tin, then manganese some copper, iron pressure iron is some iron platinum system. Okay, now there are some many, but basically for engineering use we are using the what is called as the certain nickel titanium alloys. Nickel titanium alloys, this is the thing here, nickel titanium binary. Okay, now the beauty of this is by changing the crystal composition, nickel titanium at times on carbon also, you can have different transformation temperature. So applications can go from minus 50 degrees to plus 100 degrees. Okay, but of course others are not much. Platinum based alloys are used for high temperature, is on shape memory alloy, but they are still in the is on research stage. Okay, now next is I will briefly tell you what is the difficulty in making this alloy. See, for metallurgists like us, the basic route map is the is on phase diagram. Now, the phase diagram forms the zone basis. Now, if you see the shape memory effect, right here, you can see the shape memory effect is here in a very small line here. It is a very small, narrow is on composition range. That is one is on atom percent. And so your melting has to be very strict. It is something like your semiconductor is on making, but not as tough as that. But I would say between the conventional alloys and the semiconductor is on melting. So now here, what you see is it is having very narrow range, it's on composition range, and so you should have melting some discipline, and you should also have what is called as the impurity level should be to the basic is on minimum. Okay. Then here I think I have shown in a better way. You can see the small line. So now typical engineering alloys, if you see, the composition range will be huge, like I would say 3 to 3.5%, and then 0.5 to 0.8%. But here it is the is atom percent. Okay, and and then here you can see as you change the nickel content. Okay, atom percent, because engineering alloys you'll be using the concept of this one weight percent. As you increase, the transformation temperatures will be down. You can see here it is almost minus some 100 degrees C. So normally we go up to minus some 80 degrees C. And upper range you see it is very close to 90 degrees here. Okay, and this is the microstructure. Then what are the requirements here? Now, having shape memory alloy, if you want to make it to some work for the aircraft, what are the requirements? Basically, performance, reliability under sharply fluctuating conditions. Okay, as you know, aircraft some temperature varies from minus 50 degrees to plus some 150 degrees C, and then there are G loads in this is on Tejas it is 9G, but in other is on aircraft it can be much higher, and it should sustain vibration loads. It should operate okay at all weather and meet the project goals. Project goal is what? Reduced weight and then volume, because Volume I say because once aircraft, if you just uh, open it, it is all jam packed. There is no place even to even to some service, put your hand, etc. Okay, now what we do is our testing protocol is also based to basically to fulfill this requirements. Okay, now we have used the shape memory alloys basically for the some conduit tubes. So these conduit tubes, okay, now they are some going some in the wings. Uh, as you know, the wings is a fuel tank. This is the typical conduit tube. Outside the conduit tube is some fuel, and you can see the aluminum rod, aluminum tube, and you can see the shape memory alloy ring, small ring, which will securely clamp. This is the some insulator, and then again the circuit. Or basically, shape memory alloy here is clamping the insulator, which is peak, to the tube, aluminum tube. Now, why is that we have used this? See now, using carbon fiber composite, you have to pay some penalty. Penalty is what? The static charge will be accumulating. The static charge comes because of some lightning. I think you will be knowing that lightning occurs every minute somewhere or other in the sun world. And I'm sure some of you frequent travelers by air would have also observed the lightning in the sun close range. Now, when this lightning happens, there is a static charge. When the static charge occurs, it will lead to spark. The spark can, and then fuel, it can burn the aircraft. Okay, and so to as an basically as a shield against the static charge, we have used an insulator here, peak. So the static current can be blocked here. Okay, then okay, now you can see here these conduit pipes goes here, and these conduit pipes carries what? Hydraulic oil. It can carry fuel to the, okay, it can carry fuel, or it can also carry harness wires. Okay, so this is the wing here, jig here, and of course jig is a critical part here, and it should be all close dimensional tolerances is required here, less than I would say zero point 0.1 mm. Then you can see here, this is the insulator, this is the thing. Okay, now next point is being an engineer. Why is that we have gone to shape memory a lot? Why not to other means? In fact, initially when we had the difficulty in getting it from the market, because being a high technology item, we were not getting the supplies. We tried some other methods. See, now here the requirement is once you close the wing, it is shut for nearly, I should say, at least 15 years. So for 15 years, it should work safely, and securely. Next point is why, yeah, yes, any other joints, if you try, like clamping and all, it was giving way. So that led to another some set of some problems. And once the joints give way, it is it will lead to some catastrophic failure for the aircraft. So we have used this shape memory alloys. Now I can tell you, so far the aircraft has flown in our border regions, that is in the Eastern Ladakh region. It has flown in the Eastern Kashmir, and it has flown Eastern other places. And over, I would say, we have clocked more than 30,000 flight hours, and so far, not a single failure was there. That is the kind of reliability we are getting from this. What is the sleeves? Okay, then you can see the fuselage here. Again, you see the jig here, and fuselage here is made of various stations, 1 to 1,000 stations, and each stations you will be having an certain engineer to some look after. So, and here you can see assembling it is an unique challenge here. Okay, then you can see the in the drop tank how the shape of alloys the conduit pipes are going. You can see the ring here, insulator, aluminum pipe, and inside the some drop tank. Okay, and here it is going. Okay, this is the assembly here. Okay, then here what is this? What is called as the constrained mode of recovery. Here, what you do is you are basically what you are trying to do is you are trying to cool it first, then you are trying to this one expand, deform. So now what you do is your design would be such that it is just equivalent to the one outside diameter or even slightly less. Okay, and then when you are cooling it, and then when you are okay, when you cool it, the martensite comes. What is something like 72 kg per mm square becomes something like 6 kg per mm square. You can also what is called deform it by hand, but since you are using liquid nitrogen, you are using a tool to expand it, and then when you are increasing the diameter, at this point when you are putting it here uh, inside from liquid nitrogen and then leave it in air. That is equivalent to some heating. So this will remember it the original shape and it will try to come down. So now what happens is in this is one process, the strain is constrained. When strain is constrained, you will be having clamping stress. So, and this clamping stress is a constant value. It is the constant here. The constant clamping stress is here something like 600 MPa, and this is delivered throughout the service life of aircraft. Any other joint, if you have, the clamping stress will gradually deteriorate. But here, because of its unique some properties, it will not deteriorate. That is the advantage. Okay. Now, what we thought was after this, we are having many tube joints, and this for these tube joints also we thought we can do this. Advantages, weight is very less. Earlier we had the swaging type joints. In swaging type joints, this one purpose swage and others, it was something like 100 grams. From 100 grams, this is hardly is on 2 grams. That is and then if you are having something like 1,000 joints, just see the kind of some weight savings. Okay, then you can have the some fasteners also. Okay, the beauty of this fasteners is you can give controlled torque. Okay, in many of the areas you need what is called as the some controlled some torque, and this control torque will be constant throughout the service life. Advantages of these SMA fasteners will be recovery strain, constant recovery strain, elastic strain, mm, interference is large, radial pressure is uniform throughout. No matter whatever is the size, the stress that is applied is uniform. And the tool profile is very small, and then you can do this dissimilar metal joining. Okay, now this is the S1 technology, austenite, cool into martensite, deform, 8% is the limit, and then if you warm, it will be bad. So this is inherent property of the material, and this is one repeatable. You can repeat it, okay, for several times. So what we used is the one-way shape membrane alloy. By doing this repeatable thing, you can also do have what is called applications based on this two-way shape membrane alloy. So this is the installation. You can see the tube. You can see it is cleaned, sealant is applied, and then here you can see the this one insulator peak where sealant is applied in the ID. Okay, and then okay, now it is then it is matched. It is now matched, and then it is now okay, inserted, and then you can see the SMA sleeve. You're using a tool to expand it, because it is liquid nitrogen. You can't put your hand there. Okay, now there is also another problem. He is doing without gloves. Normally we have told, since this technology was ours, we have told that, look, these things should be done with gloves, because you are dealing with the this one liquid nitrogen tank here. And then okay, this is the tool here. Afterwards it will be slit inside. You can see here, it is slit. After it is slit, it will become a tight joint. This is the way you are doing this. Okay. Then we thought we can go to the next level. Another beautiful application is the what is called as the wavy springs. So in these springs, the design thing is, you will see the spring constant. You see the deflection is directly proportional to the applied stress here, and the constant factor is the spring constant. But the beauty in this springs is wavy springs is there is absolutely no vibration at all when you have these springs in the some motors, other places. There is absolutely no some vibration. The vibration energy is being converted into the transformation energy, entire vibration energy. You can see here is being it will be some transfer. Okay, then it will be an some quiescent some kind of working. Now this idea I had got because I had seen in seismic areas like Japan, they use this shape memory alloy blocks at the sun foundation level. So any sun earthquake, the seismic vibration will be absorbed by the shape memory alloy block, and it will not get transferred to the some buildings. And so based on that, I tried this concept, and this concept has worked. But the real problem here is how to design this. Okay. Then then I thought what I should tell you what are the current efforts, international some efforts. Now, uh, what we have done is at a shoestring some budget with hardly, I would tell, hardly less than some 5-6 lakhs. Okay, we had developed some technology, but in other countries, it is much massive scales of several orders. So one such thing is the DARPA program, where there is an posting between the industry members, hmm, universities also. And I am happy because I try to involve many some institutions, colleges into our into our program. I do see now, compared to those days, now there is a lot of collaborative efforts, which I think we are going in right direction. Then there is shape memory alloy consortium, which is made of four uh, universities and three some companies. Then there is Samson program, which where government agencies, universities, is on companies. So the basic aim is this is an interdisciplinary effort. Okay. Now you can see another applications. I liked it, but anyway, we were not able to mm, replicate it. See, this is called damage healing in the composite materials. See, in the composite materials, the some problem is when you are dropping a weight on metallic part, signature is seen like as an mark, mm, some indent mark. But on composite structure, if a weight falls, it will be as if nothing has happened, but delamination will be is on inside. Now, how to find it? That is an huge thing, because you can have C scan ultrasonics, but it is having some limitation. And so here, what these people, that is University of 20, what they tried was they tried to have composite wires here, here, and then any damage here that will lead to some kind of an signal. It can be audio signal, it can be an visual signal. Okay, now this is the thing. Okay, then next is this is how to have structural health monitoring, because why we are very crazy about this is because we want aircraft typically cost anywhere from, I would say, 300 crores to something like 2000 crores, and then maintaining its structural health is one critical need. So here we are trying to see if you can, is there any advanced means to know if any defects are inside. Okay. Then another important applications which is currently being practiced is, I think, one problem with the some airports is the noise. So now there is an international guideline that noise level has to be less than 80 dB or so. I'm not too sure about the number. 80 dB, I do remember. Okay, now how to reduce the noise? One way is to have a shape member alloy here. Okay, in the engine is on outlet nasally, what we call. So here what happens is when and by increasing the diameter, the noise level can be reduced. So this is one such some technique. This is already practiced in the Boeing aircraft. Okay. Okay. Now, of course, what you see and is an application, but to do it, there were a lot of calculations, a lot of trials, a lot of frustrations. Okay, and this happens with any new sun product. So here you can see how the shape member alloy here is used to control the noise. So at the starting point, what happens is near the uh, uh, near the airport, it will simply expand. Once it expands, the decibel level will be coming down. Okay, then Lockheed Martin also did. Why not we have an bird-like flying qualities? Okay, now autonomically, why can't you fly? Okay, now most of the aircraft technologies has been basically, I would say, copied from the birds. Okay, now this is the next stage, and using this shape memory alloys by some bias. This is again a laboratory type of work wherein they are trying to have an autonomic some movements. Yeah. Okay, then how our success was achieved. So now for any success there is a lot of frustration cycle uh, is there. First is we went through basic science. We did not go through any other thing, and we went basically paper pencil route, computation of clamping stress, which is based on aircraft designers' inputs, then understanding them. Then here you need to do alloy design, which is based on above. Okay. Now for this we use some tool like some thermocol and then Calford, because you should know what is the alloy you should use. Then the process design, which is based on Cooper test. Then processing maps, we tap the IAC there, which is okay. Then fine tuning melt, which is based on computational thermodynamics. Okay. Then now based on this work, what we also did was we should involve young minds. Okay. So involving young minds at various institutes. Over six PhDs and MS thesis was produced from this project. Okay. Then what were the design issues? First was clamping of joints. Traditional interference joint design won't work. what you are doing, and instead you have to use this transformation, okay, uh, uh, enthalpy, and with this calculate the elastic strain energy, and then you have to come to the is on computing stress, and of course it's a very simple calculation. Hand calculation of the is on thermodynamics also will do. Then for springs, traditional spring constant approach, that will not work. Instead, the design should be based on minimum hmm, uh, uh, energy level. Okay, now here what you are trying to do is the trick is to convert all your design inputs to the is an, uh, uh, energy level, and then the transformation is having an energy level. Based on that, you would be you will be calculating something like energy methods in the solid mechanics. Like I'm sure some of you would be knowing this Menon-Bras theorem and all. So based on it will be something like that. And for actuators, the factors are what is the response time, work done, energy that is spent, then the alloy design and selection. Then what are the issues and concerns? Some limitation. See, any new some material is having its own plus and minus points. Okay, plus points we have spoken. Reliability is very high. Okay, and minus point is, I'm sorry. Okay, minus points are it is difficult to design, because design is based on new concepts. Then, of course, here the disadvantage is here is it is not sun sensitive, it is poor sun fatigue, and then it is costly. Okay. Now, of course, one thing unique was our cost price was a fraction of the cost price is on priced abroad. So this is a case where indigenized effort resulted in huge cost savings. So now this cannot be used as a structural member. So it can be used only for functional member. Then other thing is degradation mechanism is not known, because all that I can tell is up to 15 years you can use, but beyond 15 years what? Unless you have test done, you can't. Then each design calls for specific alloy. Then it is an integrated, holistic, deep knowledge of materials, applications, modeling process. So it is an interdisciplinary approach, because I would call aircraft as a cocktail of all technologies. Okay, so I'm sure you as the aero engineers would be agreeing to my view, and then there is a need to handle the hysteresis. Okay, that is a real challenge here. Then, what are the difference between the conventional engineering materials and the shapeable alloys? So the design is what? Design is here. It is based on the here the conventional design, but in shapeable alloys these are designed for a given application. See, you can buy from the market steel bar or steel rod, but in shape memory alloy, you have to design right from the alloy stage to melting stage. Okay, what is it you want? Then quality checks here is the standard specifications are there for chemistry, mechanical properties. Here, the application here you are clearing only for applications, not for any of these properties. Then the involvement in the component design. See, there is no need for the producers to get involved in the ISO component design. If you make a steel bar, there is no need for you to talk to designers. But here there is an you have to close involvement is required. Okay. Then coming to structural design, here it is somewhat easy in conventional alloys, linear model, but in the shapeable alloys, you are dealing with non-linear. Okay. Then you have to use DLL. Then if you see the usage, it is general purpose engineering, But here SMAs are used only for specialized because you can't use it for structural one. Then manufacturing is it is repeatable. 3 sigma level you can achieve, but here you each melt needs to be engineered. Then the QC tools, conventional lab mechanical testing is okay, but here you need sophisticated tools like DSC, XRD, TEM. Then airworthy is on clearance because just to brief you, before you put anything into the aircraft, it can be a pin, it can be a sleeve, you should have an airworthy zone clearance, and these airworthy clearances here are a challenge. Okay. Then what is the strategy we had? We thought we should create our own indigenous production facility, create a center of excellence wherein there is material modeling, application engineering lab, okay, and then of course to integrate all this. Then, of course, we had tasted some success. This is the 20 crore plant. This is an shape membrane alloy plant, first plant in our country. I would say the first dedicated plant in the some Asian continent. Okay, and maybe 1 in 3 or 4 in the world, entire world. So we had established it. Then we had the roadmap of the sun products. See, having created and plant, having created the sun facility, you should also have applications. One is conduit tube sun fittings, which you have done. Cryofit for high temperature pressure hydraulic tube sun coupling. We have done baby springs. Then the temperature control valve. The temperature control valve. Now what we do is we are using wax. The problem is after some time the temperature stability is poor, but in shape memory alloy temperature stability is high because I'm sure even in your Maruti cars earlier the temperature control valve was the wax based. After some time you will have to sort of replace it, but if it is made of shape memory alloy you can use it for throughout the service life. Then we thought we didn't go deep into it. The composite wings, health monitoring, fire, fire, fire indicator system. Because in aircraft, what happens is when there is a fire in the uh, aircraft, the pilot should know there is a fire and then he can take quick action. So now here, the traditional method is made of chromal aluminum wires. So based on some EMF input, the pilot will be having. The problem with this chromal aluminum system is false signals are very high. Okay, and so now with this shape memory alloys, false signals will be zero, and then the canopy severance system, how to severe the canopy in the okay. I'll have a slide later. I'll show that. And then stores release system, how to release the bombs and other things. Okay, the next slide I'll show that later. Then primary actuators and the adaptive wings, that is the ultimate what we thought. Of course we were able to achieve some 3 or 4, and I think by the time last year I have retired. Then this is what is called as the canopy severance system. Okay, now if the pilot is faced with an emergency and he's okay, and if his life is in danger, what he will do is the present concept of canopy civil system is it is then the some RDX, which you make it for bomb. RDX layer is here. He will activate that. It will some burst out, and then the seat ejection system is here. It will some pilot will eject, and then a parachute will be there to drop in. Okay. Now, in this present concept is frangibolt. Instead of having this RDX, we'll be having a frangibolt with a notch, with a one with a pre-stressed notch, so that once when you are applying stress there, it will break out and then it will come. Okay, so fire sensor, what is say, as I told you, we are using the SSTU chromal aluminum wire. Now the proposed scheme is SMA wire with the transformation temperature is 100 degrees. That is we can detect any sun fire there. So there is no false sun signal here. Okay. Now next is temperature control valve. From high temperature wax, we are going to the valve stem which is made of shape membrane. Okay. Then these are the XMA actuators, which is used for the this thermal control valve. And then this is the frangie bolt. What I am showing you here is the frangie bolt. This is the temperature control valve. In this frangie bolt, you can see the notch here. When you apply stress, okay, the beauty is the stress that we applied is fixed. It will not change. It will break. When it breaks, entire thing is what comes out. Now, from design point of view, you can see the shape of the alloy is having low weight. Okay, lower weight for a given S1 power. But for other actuators, weight is high, okay, and that power is also a bit higher. Okay, then is what is called the wing root some attachment. This is the wing which is attaching to the sun fuselage, and here is a bolt. Now, like this, we are having 8 bolts. Okay. Now, this is a very critical bolt because if it fails, the wings will severe. Whole mission is it will be destroyed. So here, what we do is when you are having a bolt with a predetermined torque, the torque is constant, and so what happens is you will be having absolute uh, absolute safety and then predictability, and then it will be reliable also. Okay, then coming to the stores, what I told, these are the stores, bombs, various bombs. These are laser guided bombs. You can see the air intake here. So now to release it, we are having a hydraulic system. If you have a shape memory alloy system, the release will be uh, it will be faster, and you can release it at an predetermined some trajectory also, so that you can have what is called efficient means of delivering the weapons or the stores. Okay. Then what are the current trends in the some R&D? So I thought I should share it with you because first is to find affordable shape of the alloy. It can be some stainless steel. Then how to ductilize the brittle magnetic shape member alloy. There is also magnetic shape member alloy or the Hausner's alloy. So it is having a brittle property, how to ductilize it, have proper understanding of material constitutive model, improve the fatigue life of shape member alloys, address the issues that is involved in the manufacture of shape member alloys. Then simulation of standalone or the embedded shape member alloy is on behavior. What is our uh, uh, experience? So based on what we have done, right from lab stage to the creating a unique facility, our experience is you should not treat it as off-the-shelf item. It is being highly application intensive. Each application is different, requires different alloys. End-to-end design capability is required, right from requirement to component design to alloy design, which is this one called for. Then I thought to the faculties had to throw some research topics because you can be of you can try it. It may be of some use to you. One is constitutive modeling of the alloy for a given recovery stress, temperature range, clamping stress, actuation force. Okay, this requires only basic metallurgy some knowledge, and it requires more of analytical capability. Then how to model and hysteresis as a behavior, then application and its as an architecture, then modeling of some condition ranges of the monocytic twin variants, and hence to find newer shape of the alloys. Then the basic physics that is involved in ductilizing the magnetic shape of the alloy. Okay, now this is the futuristic is an uh, aircraft. This is by NASA, not by me. So you can see it is a bird-like feature. So I thought I can share with you. I think some last year I had a chat with an Melbourne University some scientist, some professor. So I was impressed by his work. What he did was, to the leaves he had attached a very small some transducers, piezoelectric some transducers, and with the wind, and he was trying to exploit the wind speed to the current. Okay, so I think research is something vast, huge. Okay, and your thought is your limit. Now, with this, let me conclude. And this is my contact. Anyone can reach me at this some contact. I don't say no to some students, no to the some colleges. Thank you very much for the some opportunity given. Thank you again. Okay. And any it will be my pleasure to answer it. Thank you.
These participants can pose their questions.
Am I audible?
Yes, sir, you're audible. Okay. So I hope there are no questions. How can SMA used for erosion applications?
Can you repeat it, madam?
How can SMA used for erosion applications?
Okay. Now, SMA basically cannot be used for erosion some application, because the intent is not for that. The intent is uh, what is called actuating, and it is for sensing. For erosion as such, no. And then basically, if the question is whether it is having wear resistance, yes, it is having some wear resistance. But I will not recommend it for it, because it is basically is a brittle. You can't use it as a structural component. Okay, have I answered your question? So participants are basically aero background, or I think Madhu Kumar raised his hand. Yeah, Madhu Kumar. You can also use chat if you want to throw any questions. Okay, Madhu Kumar, I have a question. What is erosion control and so surface protection application? Am I right? Okay, then from Mitesh Sharma, I'm having, is it possible to modify structural behavior of stainless steel by using the shape memory alloy? Very good question. Okay, can you hear me? Hello? Can you hear me?
Sir, hello.
Yeah, can you hear me?
Yeah, is it possible to modify the structural
Yeah.
behavior?
I'm now reading this. It is fine. Beautiful question. Let me first thank you because we are doing a great research work in the stainless steel. How to have a shape memory alloy stainless steel. So basically, what we are trying to do is, let me try to tell you that the you see the shape memory effect is because of having the multicytic transformation. So we are trying to do from basic calculations to find out how to induce a multicytic sun transformation there, and from the multicytic sun transformation, how to see that it is an sun, it is an sun, it will show some shape memory effect. Now we have been somewhat successful in the sense, but it is giving only something like about 1.5% strain. But for engineering applications, we need at least 3 to 4% recoverable strain. So now I'm sure maybe the next generation will bring out this shape memory alloy based on the stainless steel. Okay, now this work is in fact it is going on. It is a hot research topic now. Okay. Okay, and then earlier the research was to go in a blind path to try something, but now it is based on what is called as the hard calculations. Okay. Yeah, Dr. Madhu Kumar.
Hello, sir. Can you hear my voice, sir? Yes,
Yeah,
sir.
sure. I can
Yes,
hear
sir.
your voice.
Actually, you are
Proceed.
talking very informative text, sir. So my question is, what is the erosion control and surface protection application in spacecraft, sir?
See, now you are not using shape memory alloy for the sun erosion work. If your some question is what is the surface sun protection you are giving, the answer is it requires no surface protection because it is basically nickel titanium, and nickel titanium, you see, it is it is having a thin layer on outside, so there is no need for any extra paint or any other treatment. Okay, then the erosion of it, if you can see, it is meeting our engineering requirement. Okay, now I can't say it is it is like any other kind of superior where erosive is on alloy, but then it is meeting our basic requirement of sustaining the parameters in the is on in the is on wear test. Okay, so I will not recommend you to use it for any wear application as such. Okay, have I answered your question?
Yes, sir. Yes, sir.
Okay.
Thank you, sir. Thank you, sir.
Okay, thank you very much.
Any more questions? I think this is the questions they have, sir.
Okay, thank
So
you very much, ma'am.
thank you
Thank
very
you.
much for the session. And on behalf of Aeronautical Department and MLR Institute of Technology, all the participants present here, thank you very much for taking your time out and being with us, sir.
Okay. Thank you very much again.
Thank you, sir.
Thank you.
So we look forward to meet you in future as well.
Yeah,
And since
sure,
you have,
sure.
yes, sir.
My pleasure.
Thank you very much, sir.
I should also thank you for giving me an opportunity to interact with you people. Okay. Thank you.
The feedback link for the session 1 will be posted in the chat window. I request everyone to kindly fill it up so that your attendance is marked. The feedback link has been given to you. Kindly fill it up.